Once again, good morning everyone. I would invite Himanshu sir to start the session.
Good morning, students. Sharing the screen. If this visible, let me know. Okay. Is this visible?
Yes, sir, it is visible.
Okay. Thank you. So, students, in last class we have discussed about the bonding portion, like ionic bonding, covalent bonding, and coordinate bonding. So today we have to discuss one more thing that is an important topic of this syllabus, that is lattice enthalpy. So anyone have any idea about the lattice enthalpy? Anyone?
No, sir.
Okay. So for the formation of one mole, either two things are there. First thing is formation of one mole, or second thing is breaking of one mole. Formation of one mole or second thing is breaking of one mole. They both come under the category of the lattice enthalpy. But what exactly happens for the formation of one mole from? First thing is from its gaseous constituent, and same thing breaking of one molecule into gaseous constituent. So both things, formation of one mole from its gaseous atom or the breaking of one mole from its into its gaseous atom, there is a release or absorption of energy. Two things are there. For example, for breaking of one mole, there is it require energy, while formation of one mole, what will it will do? It will release energy. It will release energy. So if I'm saying that formation of one mole from its gaseous atom and there is a release of energy, that is known as again lattice enthalpy. And if I'm saying breaking of one molecule into gaseous atom, it requires energy, that is again known as lattice enthalpy. So two processes are there, either the formation of one mole or the breaking up of one mole. They both are considered as lattice enthalpy just because we are considering about the lattice. Lattice, what is crystal lattice? Crystal lattice means when one and more atoms, they are combining together, they are forming a new compound. But here I'm talking about only one mole of that particular compound. So formation of one mole from its gaseous atom and there is a release of energy, it is known as lattice enthalpy. Breaking up of one molecule into its gaseous atom, it requires energy, then it is known as lattice enthalpy. Is that clear?
Yes, sir.
Okay, let's go for next, lattice enthalpy. Okay, so basically if I'm talking about the lattice enthalpy, some factors are there. It totally depend upon the force of attraction between the molecule. Force of attraction between the molecule. For example, if I'm saying there is a attraction, we have learned in the last class, there's a formation of cation, there's a formation of anion. It means positive charge and negative charge, and the positive charge was attracting the negative charge. Which force of attraction was that?
Electrostatic force of attraction.
Electrostatic force of attraction. So if I'm saying that the cation is attracting the anion by the electrostatic force of attraction, so according to the lattice enthalpy, if I'll say more attraction between these two species, it means more attraction, more attraction, force of attraction that is directly proportional to the lattice enthalpy. More attraction, more force of attraction between the cation and anion. More force of attraction between the cation and anion, then more will be the lattice enthalpy. Why? Can anyone correlate this thing? See, if two cation and anion, they are holding each other in such a way that uh, the breaking of that particular bond is more tough. So it means the energy require or energy release while forming that mole or forming or breaking that mole will be more. So it means more attraction between the cation and anion. For example, I'm talking about basic example NaCl and NaCl, Na positive and Cl negative. If there is a more attraction between these two species, these two ions, so there is a if I want to break this molecule, this attraction, breaking of this attraction will be quite tough for me. So if breaking of this particular uh, bond between this Na positive and Cl negative, that attraction bond, the energy required will be more. So lattice energy will be more. Clear? There's a formula in physics you have learned, I think, that is F is equals to K Q1 Q2 upon R square. Ever heard about this topic? This formula in physics?
Yes, sir.
Okay. So K, what is K? K is the constant, and what constant will depend upon the nature of the medium. Nature of the medium. It can be a gaseous medium. It can be gases. You cannot gas. It will be like air, air medium, glass medium, or water medium. So K totally depend upon the nature. What is Q1 and Q2? Q1 and Q2 are the magnitude of the charges. Magnitude of the charges. While R square is the distance between the charges or cation and anion. So tell me one thing. If I'm saying that Q1 and Q2 have a high value, Q1 and Q2 will have a high value, then let me know that lattice enthalpy will be more or less. See,
More,
correlate.
sir.
Yeah, you can correlate this thing and you can correlate this thing. Two things are there. Q1 and Q2 is the magnitude of the charges. It means the more magnitude of the charges, it means more attraction will be there. If more attraction will be there, it means lattice enthalpy will be more. Okay. But if I'm saying, but the condition is, if I'm saying that the distance between the charges is quite more, the distance between the charges, it means R square. I'm talking about R square. If the distance between the charges is quite more, then what will happen?
Less,
Lattice enthalpy will be decrease or increase?
less. Decrease, sir.
Decreases. Why? Because you can see here that F is inversely proportional to R square. If I remove this constant, that F is inversely proportional to the R square. It means if the distance between the cation and anion will be more, it means the cations are quite apart from the another anion, quite apart from the anion, it means there's a more distance. It means the lattice attraction force will not be that much stronger. And if the attraction force is not that much stronger, it means the lattice enthalpy will not be that much. So it means F is inversely proportional to R square. It means force of attraction between the cation and the anion. Force of attraction between cation and anion will be low. Clear this thing?
Yes, sir.
Okay, let's talk about factors. Factors which affect the lattice enthalpy. First thing is charge on ion. Charge on ions is directly proportional to the lattice enthalpy. So if I'm saying directly proportional, then what will happen? If the charge of the cation and anion will be more, the lattice enthalpy will be more. Why more? Because if I'm saying two positive ion and another is one negative ion, so the two positive ion is more and negative ion will get more attracted by the two positive ion. So if there is more force of attraction between the cation and anion, it means again, if the force of attraction is more, it means the magnitude of the charges is more. And if the magnitude of charges is more, it means the lattice enthalpy will always be more. Clear? So if the more charge on ion, more lattice enthalpy will be there. So if I do a comparison, okay, you have to tell me the answer. If I'm comparing the basic example, sodium chloride, we have taken the example last time and we have done MgCl2. Just because we are talking about the ionic compound, so we'll take ionic compound. In next class, we'll start with the covalent, but right currently we have to complete this. So tell me, I'm having NaCl and MgCl2. Compare these two species, which will have more lattice enthalpy.
For MgCl2.
Why? Give me the reason. Answer is correct.
Two positive charges and two.
Yes, very
That's
good.
why.
Very good. Just because if I talk about the Mg contain plus two charges, but if I talk about Na contain plus one charge. So charge will be more. Just leave out the Cl. First you can compare the cation. See, plus one, plus two. It means more number of more amount of charge is present on the magnesium chloride. So it means the lattice enthalpy of the magnesium chloride is more as compared to NaCl, just because positive two charge is present on the magnesium ion. Clear? Let's talk about the second
Yes.
factor. Second factor is size of the ion. Size of the ion is inversely proportional to the lattice enthalpy. Is inversely proportional to the lattice enthalpy. It means if the size of the cation or the anion is quite big, so attraction force between the cation and anion will be less. And if the attraction force is less, it means lattice enthalpy will again be less. So if I'll compare again, if I compare NaCl and tell me any element of the first group.
Mhm.
Bolo.
Potassium.
Okay, KCl. Compare these two. Comparison. See, if I'll say about the charges right now, then plus 1, plus 1, minus 1, minus 1. So charges are same. Now what I'll do? Second factor is size of the ion.
Yes, sir.
So now what can I do? I said if the size of ion is increasing, see, we have learned in this chapter that periodic table chapter. So there was the first group elements. First group element contain These elements, hydrogen,
Yes,
lithium,
sir.
sodium, potassium, rubidium, cesium, francium. Now tell me, if I'm comparing sodium and potassium, which will have bigger size?
Sodium is less,
Sodium size is less. Just because I'm going
less.
up to down in the periodic table, we have learned that number of shell will increase. If the number of
Yes,
shell will
sir.
increase, it means that if the number of shell is increasing, it means that sodium and potassium will be more bigger in this size as compared, just because of the trends but we are following. So if the potassium have a bigger size, and I told you, if the size will increase, lattice enthalpy will decrease. So it
Decrease.
means, now compare NaCl and KCl, which will have more lattice enthalpy.
Sir, NaCl.
NaCl, very good. Just because Na is smaller in the size, smaller the size of ion, greater will be the attraction and greater will be the lattice enthalpy. But one thing, if they both factors are showing the different value, just imagine charge and ion is directly proportional to lattice enthalpy is showing that the lattice enthalpy of one element is more, while the same on the basis of size is less. Then which will be the dominating factor? You'll say that this one, charge on the anion, it will be considered as the dominating factor. You'll use charge on the ion factor and everything will be right. Clear? So sometimes it
Yes,
happens
sir.
in some compounds, there's a possibility of having some sort of uh, conflict, like charge on the anion is more, so lattice enthalpy was more, but the size of that cation was quite less, quite more. So in comparison, it was less. So the dominating factor will always be charge on the ion. Okay, let's do a question. Compare I think this is in your book. Okay, compare these two elements and tell me which one. This is Mg magnesium oxide. Now tell me which one have more lattice energy. Fast.
Sir, MgO. MgO.
Okay, MgO goes for the first. Okay,
Yes,
second,
sir.
second,
CaCl.
CaCl2. Okay, and then third one is NaCl. Just tell me the reason.
Sir, MgO is charge plus 2,
Mg
sir.
plus 2 charge. Okay, oxygen is minus 2, A plus
Yes,
2,
sir.
minus 1, plus 1, minus 1. So you can compare the easily charges and then it will be done. Okay. Some things you have to remember, that if condition is, if lattice enthalpy is more, compound will be more stable. Stability increases. Why increases? Just because if the more attraction is present between the two species, you cannot break the bond easily. If you cannot break the bond, it means the bond is quite stable. So if lattice enthalpy of the molecule of a compound is more, it means I'm talking about the stability of the compound is more. Okay. Second thing, melting point is also more. Why? Melting point is also more as higher, you can say, just because it need to break up the bond to get melt. So just because of that, the lattice enthalpy will be more. So these two factors you have to remember. We'll talk about the solubility and all other things later on. So till now, if there is any doubt in lattice enthalpy, you can ask. Anyone? Or else I go for the calculation of the lattice enthalpy. Anyone? Any doubt? Yes or no?
No, sir.
So should I move on?
Yes, sir.
Okay. So let's talk about the calculation of the lattice enthalpy. Calculation of lattice enthalpy. So for the calculation of the lattice enthalpy, we have Born-Haber cycle. And what is Born-Haber cycle? It totally depends upon the principle. And the principle behind this Born-Haber cycle is Hess law of constant heat summation. Hess law of constant heat summation. So, ever heard about Hess law?
No, sir.
Okay. So, if I take a basic example, just imagine that any compound, any of the reactant is converting into the product, and there is a change of energy, that is delta H. Just because we know that the reaction either it will be endothermic or exothermic, just give me a quite difference between the endothermic and exothermic fast. Anyone know endothermic, exothermic?
Yes, sir.
What is endothermic and exothermic?
Sir, energy
See the word endo.
releasing and sir,
Ex
energy releasing and energy
absorb. See,
absorbed.
endothermic means there's an absorption of energy. Na? There's absorption of energy. Well, if
Yes,
I talk
sir.
about the exothermic, there is a evolution of the energy, or you can say liberation of the energy. Okay, so these two terms are there. So if I talk about the absorption or the emission of the energy, it means I'm talking about any of the reaction. It can be endothermic, it can be exothermic. So I'm calculating the value of delta H. Delta H change in enthalpy. Okay, so according to the Hess law, what is the constant heat summation thing? That just imagine if I'm talking about the basic net reaction. What is net reaction? Net reaction is reactant is converting into the product. But in case I'm saying the reactant is converting into the A, now A is converting into B, now B is converting into C, now again C is converted into the product. Okay. So ultimately what we got that reactant is converting into the product now. Either it can be in the steps or either it can be in the net form elementary reaction. So if I'm talking about the reactant is converting into the A, it means there is an energy change. So I'm taking this energy change as delta H1. If when A is converting into B, that I'm considered as a delta H2. B is converting into C, I'm taking it as a delta H3, and C is converting into the product, I'm taking at delta H4. So according to the Hess law of constant heat proportion, Hess law of constant heat proportion, what exactly happened? It says that whether the reaction occur in single step or in the multiple step, the energy change will be same. It means according to the Hess law that delta H is equals to delta H1 plus delta H2 plus delta H3 plus delta H4. So according to the Hess law, that if a reaction is occurring in the multiple step, the energy change will be equal to the net reaction energy change. It means the delta H will be equals to delta H1 plus delta H2 plus delta H3 plus delta H4. So this is the statement of the Hess law. We have not started the Born-Haber cycle right now, but the principle of the Born-Haber cycle on which it depends totally, that is heat loss, Hess law of constant heat submission. Okay, so do you understand what is Hess law now? Anyone? Any doubt in Hess law?
No, sir.
Okay, so I'll take example. See, this is quite important what I'm saying right now. Okay, so just consider a reaction that is Na is reacting with half Cl2. It is forming NaCl. If I'll take it as Cl2, then this will not be considered as 1 mole. We are talking about 1 mole only. So sodium is solid in form, chlorine is gaseous in form, NaCl is again solid in form just because it's an ionic compound. So this is a net reaction, and net reaction with enthalpy change I'm considered as delta H. Delta H is the enthalpy change. Okay, so if I'm talking about the Born-Haber cycle, that this reaction sodium is not easily converted into the NaCl. We have learned in the ionic bonding that Na positive will form Cl, negative will form, and the positive will attract the negative, and then they will form NaCl. So it means first sodium must convert into the positive ion, that is cation. Cl must contain the negative ion. It means the sodium must donate the electron and Cl must accept the electron. So if sodium must attract the electron and Cl must means donate the electron sodium and Cl will attract the electron, it means first they must convert into the ionic form. See, Cl2 is in the gaseous form, so it's okay. But for converting the sodium into the cationic form, first sodium must be converted into the gaseous form. So I'll consider it as steps in this particular, I'll consider some steps in this particular reaction. So if I talk about the step one, first step will be that sodium solid must be converted into sodium gas. So just tell me fast one thing, that the process is solid is converting into the gaseous form. So the solid is converting into the gaseous form. What is the name of this process? Solid convert into gas. Anyone know? That is sublimation. Okay, just give me before this, just tell me something. Solid is converting into the liquid. What it is known as? Solid is converting into liquid.
Melting.
Huh? Melting, yeah.
Melting.
And liquid is converting into the gas.
Evaporation.
Evaporation, you can say vaporization. Okay, solid is converting into the gas.
Sublimation.
Sublimation. So same thing is occurring over here now. That sodium solid is converting into the sodium gas. So the sodium solid is converting into the sodium gas. It means there is a change in energy just because this reaction is an endothermic, sorry. Just because we have to heat up this solid only in that particular time it will convert. So the process is sublimation and an endothermic process is there. So it means first is delta sublimation is equal to be positive just because the energy is absorbed. This is the step one, that the sodium solid is converting to sodium gas. There is a sublimation of the energy that will be considered as positive just because the reaction is endothermic in nature. The second step will be step second. Step second is now sodium gas will convert into sodium ion. So it means if it is converting into the sodium ion, there must be ionization energy. Ever heard about ionization energy? That one of the sodium, like when any atom is giving out the electron, it requires the energy. So if it requires the energy, again energy is absorbed. So ionization energy will be positive. Ionization takes place. Now cation is formed. Now we'll talk about the step third. We'll talk about the step third. Half Cl2, which is already present in the gaseous form, will convert into the Cl. But I'm talking about when we have to convert the Cl2 into the gaseous atom. Okay. So, or you can say directly this. Cl2 is converting into Cl just because we need only in any Cl, only one Cl is present. So I need only one Cl. And here I have Cl2. So I need to break up the bond. So for dissociating the bond, for bond dissociation, what I require the energy. Okay, so if I'm talking about one Cl, so I need to put half over here. So I'm breaking the Cl2 bond. So the energy I require, that is bond dissociation energy, and we require the energy. So it is considered as again positive. But one more condition. If I'm using half on the left side of Cl2, then I'll take the value of bond dissociation will be as half. Sorry, I need to take the bond dissociation energy as half, just because I'm considering about the one molecule, because half molecule of the Cl2 is taken. So you can directly write over here if you want to write that half molecule, half mole of Cl2 is taken. So bond dissociation energy will be half. This much is clear.
Yes, sir.
First step, what we have done that the sodium solid is converting into the sodium gas. Then sublimation occurs, so it will be considered as positive. Second step, what I have done, that sodium gas is converting into sodium ion. So it means it released electron. So that is ionization energy. So energy was again required. So it is taken as positive. Third step, half of the Cl2 molecule gives out the Cl gas. And there is a breaking of the bond, so it is considered bond dissociation energy. Next one is step number 4. Step number 4, that is Cl2 gas is converting into Cl gas. So, no, sorry, it's not Cl2 just because we have converted into Cl. So it will be considered as Cl negative. So now it means if I'm talking about the negative, so now the Cl have accepted the electron. Whatever the sodium in the last step here, the sodium have given the electron. What happened here? Sorry, here sodium have given the electron. So if the sodium have given the electron and that electron is gained by now Cl negative ion. So when, okay, the process, just tell me the process fast. When any of the isolated atom, the isolated gaseous atom is accepting the electron, the process is known as accepting electron. No, no one knows.
For electron affinity.
Yeah, either you can say electron gain enthalpy. Okay, so here delta H, electron gain enthalpy, will be taken as negative. Till now, when I was talking about these three, like sodium sublimation energy, it was positive. Ionization energy, it was positive. Bond dissociation energy, it was positive. But now when the electron is added, when the electron is added, then it means the energy is released. So if energy is released, the process is considered as exothermic process.
Exothermic.
So it means now the delta Hg, yani electron gain enthalpy, is considered as negative. Now positive is formed, negative is formed. Cation ions are ready. Now talk about the step number 5th. Step number 5th is now Na positive will attract Cl negative. They both are in the gaseous form. And then it convert into NaCl solid. Okay. In this step, energy is released. Why? Because when the new, because it is a attraction force. It is a attraction force. And when the new form, I told you in the starting of the lattice energy, what I told you, that what is lattice energy? First, either the formation of 1 mole or the breaking up of 1 mole. Now I'm talking about the formation of 1 mole. It means the sodium chloride was reacting with Cl negative. Any positive was reacting with the Cl negative, forming the sodium chloride. So it means there is an attraction force between the Na positive and Cl negative. So when there is an attraction force between the Na positive and Cl negative, there is an amount of energy, certain amount of energy is released. And when the certain amount of energy is released while forming the new attraction, the energy is known as lattice energy, and delta H lattice is equals to negative just because the energy is released. So now according to the Hess law, delta H, these were the 5 steps. Now I'll talk about the delta H. So first process was delta H sublimation. Second process, ionization energy. Third process, half of bond dissociation energy. Fourth process, delta H Eg, yani
Electron
electron
gain.
enthalpy. Very
Gain
good.
enthalpy.
And last one is delta H lattice. So for calculating the overall enthalpy change, we need to add all the things: sublimation energy, ionization energy, bond dissociation energy, electron gain enthalpy, and lattice energy. So now for the calculation of the lattice enthalpy, we don't have actual formula, but we have created the formula in such a way that we have taken all the amount of energy, then we can easily calculate the enthalpy change. So is this clear?
Yes, sir.
Just go through it once, fast, quick. Just go through it, see it once. If any doubt, then ask. Just because this is the most important topic in the lattice, in ionic bond, we can say this is the most important topic, that bond dissociation energy, how it happen, how lattice energy affect, and how what is the calculation of the lattice energy. So sometimes in the books directly given, like if you'll say bond Haber cycle for the NaCl in your book, you'll see that it is directly given, like Na is converting to S, then G positive, then Cl, and they have now added and form the delta H. So if you'll go step by step and showing the steps and you can write the things, it will be more easier for you to learn and more easier to for you to remember the things. Done? Sometimes you can take this screenshot if you want to take the screenshot, like any other thing, but you think that important for you. Okay. Should I move on?
Yes, sir.
Okay. Tell me, what was the principle I told you on in the last class regarding the solubility? Like, dissolve, like. What was the meaning of this? Anyone remember? Like, dissolve, like. See,
Polar solute will dissolve in
yes, dissolve in.
polar solvents, and
Yes, polar solute will dissolve
non-polar
in polar
polar
solvent.
solvents.
Very good. And non-polar solute
Non-polar
will
solute
dissolve in. Okay,
dissolve in non.
non-polar solvent. Very good. So, if I talk about the dissolution of the polar solute to the polar into the polar solvent, I'm non-polar solute into the non-polar solvent. Just because I'm talking about the ionic compound right now, I'm talking only about the polar solute and polar solvent. So, what is which solvent is considered as the universal solvent?
Water.
Water. Okay. So, how there's a dissolution of the ion takes place? Okay. So, just basically understand the fact. I'm talking that I've taken a ionic compound and I put that ionic compound in water. Okay, ionic compound is again polar, water is again polar. But how does polar attraction occur? So what will happen when I put that NaCl in the water? What exactly happen? Pole of water molecule. These are the water molecule. Sorry. These are the water molecule. Negative, positive. Just because why I'm saying negative, positive? Just because in water we have oxygen as taken as the negative ion while hydrogen is taken as the positive ion. Okay, so here I'll take Na. Here I'll take Cl. So Cl is again just Cl will be positive, negative, here positive, negative, positive, negative, positive, negative, and positive, negative. So what exactly happen when we try to dissolve the ionic compound in water? There is an attraction force between the Na and Cl. Okay, just because we are talking about the lattice enthalpy, we are talking about the electrostatic force of attraction. So whenever any compound is dissolved in a polar solvent, it means polar ionic compound is dissolved in the polar solvent, what exactly happens? There will be a separation of ion takes place. There is a separation of ion takes place, and when there is a separation of ion takes place, this process is known as solvation of ion. Solvation or of ion, or you can solvation, or second term you can use here as hydration. So this attraction force between the Na and Cl negative start breaking off, and when it start breaking off, what exactly happens? It start dissolving. Why? Because Na is a positive part and Cl is the negative part. Now the positive part from this particular side attract this negative of the Cl. This negative of the Cl. But on the left hand side, the negative part of the water molecule will attract the H positive, Na positive. So now positive and negative, they both get separated in different direction, and they like the bond will again break and they start dissolving into the solution. So now how the polar solute is dissolving the polar solvent, it totally depend upon the strength of bond. So if I'm saying, see, if I'm saying the condition, okay, you have to correlate again with the last topic. I'm saying lattice energy is more. Lattice energy is more. Okay, one more thing. While forming the while forming this hydration, there is a certain amount of energy is released. Here, certain amount of energy is released. Okay, and that energy released is known as hydration energy. Energy release is known as what? Hydration energy. And now I'm saying that if the lattice energy is more than hydration energy, if the lattice, first condition is if the lattice energy is more than the hydration energy, then let me know the compound will dissolve or not dissolve.
Dissolves.
It will dissolve. I'm saying for the dissolution, there must be a breaking of this particular bond. But I'm saying the bond, the lattice energy between this Na or Cl, it means they both are quite stable. So if they are stable and the bond is not breaking, so it will not dissolve. Basic thing.
Yes, sir.
It will not dissolve. The condition is if the attraction force is more and the ions are not getting separated, so they will never dissolve. It means if the hydration energy is less and lattice energy is more, there is no dissolution, or you can say solubility is less. Solubility, no solubility liquid. Second condition, just opposite. Hydration energy is more than lattice energy. Hydration energy is more than lattice energy. Now tell me, will it dissolve?
Yes, sir.
Yes, just because the bond between the ionic compound will easily break. It means more solubility. Solubility will be considered as more. Clear? What is hydration energy?
Sir.
What is hydration energy? When the ionic compound is dissolved in the polar solvent, it dissociates into its ion. So when it dissociates into the ion, certain amount of energy is released. And this certain amount of energy is considered as what? It is considered as hydration energy. So if I compare about the two things, that if the lattice energy is more and hydration energy is less, it means the bond will not easily break. And if the bond will not easily break, it means there will be no solubility or less solubility or approximately negligible solubility. But if I talk about the hydration energy is more than the lattice energy, it means the solubility of the compound is more in the polar solvent. Clear? Clear?
Yes, sir.
Okay, some variation, just basic variation. So I'll give you one question then. Variation is size of the cation, size of the ion, just simply size. Size is inversely, size of the cation or the ion is inversely proportional to the hydration energy. It means if the more bigger the size of cation or an ion is there, I'm talking basically we talk about cation. Okay, more bigger the size, less will be the hydration energy. Okay, so I'm giving you a question. The question is Li positive, K positive, or Fr नहीं फ्रेंच नहीं देंगे और CS positive. Arrange these in the terms of hydration energy in decreasing order, increasing order of hydration energy. First, tell me the answer.
Can you repeat the question?
Hmm? See,
Question, sir. Question.
this is okay. This is a series. First group elements. Okay.
Yes, sir.
Take positive sign on each element. And now tell me, I'm saying if the size is more, hydration energy is less. So tell me which of the element will have least hydration energy and which of the element have highest hydration energy. This is a series.
Cesium have
Cesium have.
least energy, sir. Least hydration energy.
Yes. See, cesium, just because cesium is coming in the down the periodic table. So cesium have bigger size. Cesium have bigger size. If it have bigger size, it means less hydration energy. Very good.
Yes.
And which will have the maximum hydration energy?
Lithium, sir.
Lithium.
Lithium will have highest hydration
Hydration.
energy. So this these type of question is will be asked in the exam. So you need to tell me, you need to revise the things. Okay. Or you need to, if you need to like arrange in themselves in the decreasing or the increasing orders. So in the increasing order, it will be increasing order. It will be minimum first, cesium, then potassium, then lithium. Sign you can arrange according to yourself. Okay, whether increasing or decreasing, whatever it is there. So just remember these type of question is easily asked. Okay, just a simple question I'm writing here. Na positive, Rb positive, Fr positive. Fast.
Francium. Least, sir. Rubidium next.
Francium
Next.
is first one is सबसे least.
Yes,
Least
sir.
one. Least one is
Francium.
Francium.
francium. Okay, and then
Rubidium.
Rubidium.
okay, then sodium.
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 Okay. So it means you have to remember what you have to remember. You have to remember only this thing. If the size of cation is more, hydration energy will be less. Clear?
Yes, sir.
Yes, sir.
Okay. So if I'm saying I'm going any more example, this one is okay. Okay. So now what you have to do? See, we have discussed about the characteristics in the last class. Like ionic compound are solid in nature, ionic compound have high melting boiling point, polar,
Yes,
they are
sir.
polar in nature. We have discussed all these things, huh?
Yes, sir.
Okay, so today we have completed the ionic bonding. We have certain example. We have, in the first class we have done the ionic covalent coordinate, basic things. Then we have discussed about the what are ionic bonds, what is electrostatic force of attraction, and now we have discussed all about the lattice
Lat.
energy and what are the factors which affect the lattice energy, and the things like Born-Haber cycle, how you can calculate the Born-Haber cycle. Okay, now okay, now you can ask if you want to ask any of the question regarding the today's session. It can lattice energy, bond diffusion energy, ionization energy, whatever you want to ask. If you have any doubts, you can ask. Anyone, any doubt? No doubt.
No, sir.
Okay. That much is enough. Just because if I'll start the covalent bond right now, it will be too much mixing up. So ionic bonding is just done. Yeah, nothing is left in the ionic bonding. You can do the questions. I'll send some questions. You can do them, and next time I'll start in the next class tomorrow. I'll start the covalent bonding. Some factors affecting the covalent bonding, and apart from that, we'll start. I think covalent bonding is quite easy, and a short topic. So we'll start the coordinate bond also. Okay. So till then, enjoy and complete this. And remember, you have to revise every day. Just because if you'll not revise it today, you'll forget it. Definitely, that is called a sort of retrieval failure. So just revise it and see you in next class. Thank you so much.
Thank you, sir.
Thank you.
And just join them. Join the next class now. Okay.
Students, join the next session, next link.